This is an example video for how to draw the vectors for the inclination investigation to properly add the vectors together using visual vector addition. Here I have some example data for a water bottle that has a mass of about 450 grams. I have example masses that would read on the digital scale and forces on the spring scale. And then these masses converted into a force reading using the dividing by 100 grams per Newton. So then we are going to, for this process, use a conversion of 1 centimeter equals 1 Newton. That works well with the size of paper and the size of forces that we're dealing with here. So the students will need a ruler and something to draw with. I'm going to use markers because they're easier to see in the video. So let's do the 30-degree one together. So we have 30, 45, and 60 are the ones that the students are going to draw. And each of these triangles has the bottle here and 2 guidelines. And these guidelines are set up so that the students will draw the vectors and they will be able to add them together while doing that. So first we're going to take our spring scale mass and our spring scale force, and we have 2.3 newtons for 30 degrees. So I'm going to measure from this corner of the 2 guidelines, and I'm going to measure 2.3 centimeters because that's equal to 2.3 newtons. So I line it up, 2.3, and draw a line to that corner that's 2.3 centimeters long, and add the arrow showing that it's down the ramp because it's balanced out by the force the spring scale is applying up the ramp. And we label that 2.3 centimeters equals 2.3 newtons. And that's our first force that we have measured. The next one we're going to draw is the digital scale force. So we measured a mass of 389.7 newtons, grams, and converted that to 3.897 newtons. That's more sig figs than we can do on our ruler, but that's what we're going to, so we can just round that to 3.9 newtons and 3.9 centimeters. So I'm going to measure again from this corner of the 2 guidelines, and I'm going to measure out 3.9 centimeters, draw a line, and draw the arrow to show that that vector is pointing into the incline, perpendicular to the incline, because it's balanced out by the scale pushing out of the incline. At this point, we can label that, and we had 3.9 centimeters equals 3.9 newtons. And at this point, you're going to have the students do this for all 3 angles and then make some noticings. And they should notice that the top of the first arrow ends up right above the bottom of the second arrow, or notice something about that spacing when they have all 3 put together. And that's when you're then going to present that vectors can be visually added together by creating this one-way pathway, often called tip-to-tail vector addition. But I like to talk about it as a one-way street with a definite beginning and a definite end and nothing in between, and you can follow the entire path and get from there to there, or you can do a straight line from the beginning to the end, and that would be equivalent because it would give you the same amount of distance traveled in the same direction as if you did this and that. You start at the same place, you end at the same place. So you can draw that vector from the start of the first one to the end of the last one. And that gives us our sum of these 2 vectors. And we can measure that, and we see that it is 4.5 centimeters. So we can measure 4.5 centimeters. And we know that that equals 4.5 newtons because that's our conversion from our drawing length of our vectors to the magnitude of the vectors in newtons. And this makes sense because the weight of our water bottle in this case was 4.5 newtons. So the gravity force, which is the sum of the 2 components, should always be 4.5 centimeters or 4.5 newtons on all 3 of these. Now you're going to do an example with a mass other than what the students have, and then they're going to first draw the measured forces, see what they notice, and then draw the sum vectors for each of those.